In this video, I want to talk about something called quantum numbers. But before I get into that, I just want to go over the definition of the orbital. So basically, an orbital is a mathematical wave function. So an orbital is a mathematical wave function, and that can be represented by this Greek trident looking thing called psi. And so basically they represent a probability distribution. There's a probability of finding the electron 90% of the time in this electron cloud as shown here. So this is the quantum mechanical model of the atom as I discussed in that previous video with Schrodinger. What's also important to keep in mind is that orbitals are not actually real. They're sort of just how electrons move. We use math to represent how they move. And they move really weirdly because of their wave-like characteristics. If you recall from what I talked about de Broglie in the last video, all matter has wave-like characteristics. It's just that the larger your mass is, the more negligible it is. So for electrons, since their masses are incredibly small, their wave characteristics are quite important. So that's just how they move. They move very, very weird because they act both as a particle and a wave, which is hard to imagine. So let's take a nice deep dive into quantum numbers. What are quantum numbers and why do we care? Quantum numbers basically allow us to locate an electron. So let me just write that here. Quantum numbers. They basically allow us to locate or like find maybe like where the electron may be. So locate where the E may be. And they also can tell us the general energy of that orbital. So the energy or of that electron, I should say, in whatever quantum numbers that can be used to represent that. So basically there are four, and actually before I get into that, the way to think about quantum numbers is sort of like a mailing address. So you could have the province down, the city, the street, and the house, right? So there are four quantum numbers, and each of them you can sort of think as the province, the city, the street, and the house to basically locate the E. And what is important to keep in mind is that every electron has its own unique quantum numbers. So all electrons, all E have their own quantum numbers. So what that means is an electron can, let's say, two electrons can be in the same province, they can be in the same city, they can be in the same street, but they cannot be in the same house. Basically, so the way to think about them is they don't get along. They can never be roommates. So that's basically it. Every electron has their own quantum numbers. So let's get right into it. The first quantum number is called a principal quantum number. And basically, this is just the period number in the periodic table. So I'm going to try to draw a periodic table here. Yes, sort of. Right? Yeah. Okay, it's terrible. Anyways, so it's just the period number. So this is period 1, 2, 3, 4, 5, 6, 7, and so on and on, up to like 7, right? So basically, that's basically it. It's just the period number, and it tells you the main energy level it is in. The main energy level the electron is in. And so this principal quantum number is represented by the letter n, and it's basically an integer, positive integer that ranges from 0 to 7. So So that's basically it. It just tells you, what main energy level it is. It's very basic. This is again like the province. What's the main energy level? Think of that as just the province. And the maximum amount of basically like the most amount of electrons that can exist at any possible energy level is represented by 2n squared. So if your energy level is 2, plug that in. That's the most amount of electrons there can be in that specific energy level. The next quantum number is called the orbital shape quantum number. Now, this one looks and is a little bit more interesting. So basically, this defines the shapes of the orbitals within the principal energy level. In other words, it defines the shapes of the subshells within their principal energy level. So if you recall from the previous video where we talked about the multiple line spectra and that weird looking thing when you do the line spectra for elements greater than 2 electrons, in a certain color there would seem to be multiple bands instead of just one, which Bohr found with hydrogen, right? Because he was only playing around with one quantum number. He didn't know about this idea that, well, there could be subshells. So basically this defines the shape of the subshells. Shapes of the subshells. Now, the values of L, and because these are quantum numbers, right? These numbers are going to represent the shapes. So the values of L can range from 0 to n minus 1. In other words, it is dependent on the principal quantum number. Because remember, n represents the principal quantum number. I'm just going to call that P. It is dependent upon the principal quantum number. So what does that look like? So let's say, so let me write it down actually. So when L equals to 0, and I'll write these all down. L equals to 1, L equals to 2, L equals to 3. When L equals to 0, this is given the letter S for the subshell. This is given the letter P. This is given the letter D. This is given the letter F. This may look a little familiar to you. If you've done electron configuration in the past, maybe if your teacher has taught it to you, you may recognize SPDF. If you haven't learned it, don't worry. I'm going to be making a video on it, and that'll sort of become like full circle. So these are given specific names: sharp, principal, diffuse, and fundamental. And if you're wondering which one's which, s orbital, right? So this is when L equals to 0, this is when L equals to 1, this is when L equals to 2, and this is when L equals to 3. So you have a SPDF, and you can see as the numbers increase, the orbitals or the subshells start to look even weirder. So let's do an example. Let's say n was equal to 3. If n was equal to 3, then L can be equal to 0, 1, and 2, right? Because it's 0 to n minus 1. 0 to n minus 1. So what does this mean? 0, 1, and 2. Well, that means that there are 3 different shapes. So this means, if we look at this, this means that there are 3 different shapes of orbitals or slash subshells in the 3rd energy level. And that's pretty much it. So that's the orbital shape quantum number. It basically allows you to sort of define the shape of the subshell. And as you can see, it gets more complex, as I mentioned earlier, more complex as the L, or the orbital shape quantum number, increases. Now the 3rd quantum number is called a magnetic quantum number. So basically, This quantum number indicates the orientation of the orbital, but also the number of orbitals that are possible. So indicates, let me give some space, indicates the orientation and the number of possible orbitals. Or I should say orientation of the orbital. Orientation of the orbital. Number of possible orbitals. So the values of the magnetic quantum number range from negative L to positive L. So let's do an example. Let's say if L equal to 1. So example, if L equal to 1, what would be the values of this letter here and this magnetic quantum number? And it's written as M and then the subscript L. Pause the video and see if you can figure that out. So I'd mentioned it's from negative L to positive L. So what that would look like is basically all the numbers, all the integers. I should write that right here. Integers, because we're not gonna write all the decimal points and anything, just the integers. So it's all the integers from negative L to positive L. So that is negative 1, 0, 1. And we can see that here. So if L equals to 1, we know that this is the p orbital. And the p orbital looks like the dumbbells. So this is the p orbital right here, p. And we see that when L equals to 1, that's what it looks like, these dumbbells. And also the ML, or the magnetic quantum number, indicates the orientation, also how many there are. So you see there's px right here, there's pz, and there's py. That is the orientation. These little things you see on the graph right below, they indicate the orientation. So that's basically the magnetic quantum number. If I said, let's say L equals to 2, what would that be? Well, that would just be negative 2, negative 1, 0, 1, 2. How many, orbitals are we dealing with? That's, I should do this in the blue. That's 1, 2, 3, 4, 5. And if L is 2, this is the d orbital. So we see here, this is the d orbital. So negative 2, right? So we see the 1, 2, 3, 4, 5. And these are all the different orientations it can possibly have. And you sort of get the point, but I'll do it once more. Let's say I said, L equal to 3. The ML values could range from negative 3, negative 2, negative 1, 0, 1, 2, 3. How many values are these? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Each with a different orientation, and these are the possible ones they could be. And this is the F block, or the F orbital. So that's basically the magnetic quantum number. Indicates the orientation and the number of possible orbitals. Next one, and the final one, is the magnetic spin quantum number. By far the easiest. Basically, every electron has its own spin. Either spins half up or half down. Negative half down. So this is up and this is down. And this generally, when you write your quantum number, you'll put your principal quantum number. So I'll write it. So basically I'll be showing this in the next video, but basically it would look like principal quant, I'll shorten it, principal quant, so in a bracket, principal quant, I should have just done this, whoops. Basically, in parentheses, you write like coordinates for quantum numbers. Basically, it's N, L, ML, and then finally MS, and that's the subscript. That's how you would write the quantum numbers for one electron. And I'm going to be showing this in the next video. But basically in any Pacific orbital, so let's say if this was my Pacific orbital, some energy level, and an electron would be half up and another would be half down. This is the way you show it. You do this weird half arrow to show one electron. These are each an electron. So in the same shell, one must be up, one must be down, and this is to avoid electron repulsion. So I've already sort of taught you some electron configuration, but that's basically it. There are these 4 quantum numbers I just showed you, and they're all about locating the electron. You can think of this as, first finding the province, finding the city, finding the street, then the house. And it's important to keep in mind that every electron has its own quantum number. And yep, that's pretty much it.